Hello everyone, I'm happy to see everyone here. I'm Alex Honchar. And the first question before I introduce everything, the topic, myself, and blah, blah, blah. Does this words, time series, deep learning sound familiar to you? Do you already have some experience with one of them at least? Okay, who worked with time series? Now, before? Okay, most of you guys, that's great. Deep learning, but not time series. Vision, language. Okay, that's good. And there's some intersection, which is nice as well. So basically, as you might guess, today we're going to talk about time series, deep learning, and my thesis for today that we'll together, I hope, try to prove or disprove if deep learning is something what's the last thing we can create for dealing with time series, at least the time series we have today. Two words about myself. I'm working in machine learning field for the last 6 years, and I was doing different things, mostly deep learning. I was lucky enough to jump into the hype and kind of dive deep into it. And my main focus now is healthcare and consulting. So basically, I'm a co-founder of 2 companies. One is developing medical devices for ECG analysis, electrocardiogram. And second is consulting company where I have to deal a lot with this time series because that's what the industry wants. Time series from the sales, finance, manufacturing, wearable devices, and a lot of other things. So that's why time series is the thing that I'm dealing with every day. And I'd like to share some experience, some insights, hopefully some controversial things as well. Yeah, that's how people see me. Sometimes when I say, oh, I'm deep learning, I'm doing deep learning, especially taking account that I live in Italy, it definitely looks like this. But to me, deep learning actually looks like this. Basically, we have some matrix multiplications. We just combine them into the different forms, different combinations. So that's how I see it. And I hope we all know that deep learning really made a lot of nice results in another fields. I think this GIF you all already have seen. Big gun, generative network, generating nice-looking faces. Thanks, deep learning. Natural language processing. I think you all are, I don't know, scared, not scared about the fake news that this GPT-2 can generate. Again, thanks to deep learning, at least at some point to deep neural networks. Recommender systems. I know that we study mostly collaborative filtering, but actually in context-based recommendation, we again have deep learning. Sometimes it fails, maybe not that horribly, but I'm not satisfied with my Netflix, so I don't see it like this at least. And of course, with speech, with sound, with voice analysis, again, we have deep learning. And one of the last cases of generative stuff, we can fake the voices and actually make some scams. And I did on purpose that I mentioned a lot of things about generative modeling here because actually today we're also going to speak about generative modeling for time series and how it drives the advances here. But all this hype stuff, but actually with time series analysis we don't have much hype. Okay, maybe this character, this YouTube blogger, showing a lot of interesting stuff, but not much deep things, actually. And that's why my goal for today is try to show you more on time series. But actually, obviously, I'm not the first one who's asking this question. Basically, I borrowed the title for the conference from another conference 5 years ago, where it was a panel discussion if in Israel, if deep learning is the final frontier for signal processing. And I like it a lot, and that's the question I'm asking myself often. And I have an answer for myself and asking for you, like at this moment, what do you think? Basically, yes or no? Who thinks that yes? At least some intuition feeling that deep learning is something what is the top today. Okay, who thinks that let's rely on mathematics, on stochastic calculus or something like this? Okay, and other guys, you're waiting for the presentation to have the answer. Okay. Good. Basically now, the plan is I'll just go relatively quickly through the main topics we deal in time series analysis. And actually, when I'm giving this speech already for several times, and I iterate it every time. And now I came up to the idea I would like to show you the comparison that we have some classical models and how deep learning, how neural networks actually naturally come out and are based over the classical applications. So let's start. First block is time domain analysis, basically time series that we analyze through the time for classification, regression, and standard stuff. When I'm saying time domain analysis, I mean that there are time series that actually look nice visually. For example, the first picture is the classical dataset for airplane ticket sales, I guess. And basically, if you want to forecast this curve, you can do it by hand. You see there's some seasonality, you see the trend. You can even draw by hand your own prediction over the first picture, and most probably you'll be right. It's clearly seen. The same, what I'm working is ECG, electrocardiogram. If you're a doctor, if you studied how your heart works and how it generates the electrical, how the circuit of your body works, basically you just look at it and you see, okay, this is the part that is healthy, and if I see something visually, it's not healthy. And I see it in the time domain. That's why I'm saying time domain. And how do we used to deal with this kind of data usually? Basically, if it's visual, we can create some geometrical features. We can make some mathematical model, we can make some formula. If it's something like time series 2 forecast, we can decompose it into, for example, some periodicity and the trend. So you have the trend itself, you forecast the trend. You have periodicity, you forecast the periodicity. There's some statistical models. And the main groups are like this. The core idea of the statistical models are mainly linear. So basically they assume already that there's some linear formula that models, for example, the sales time series. And there are another nice examples, more like real world. For example, if you talk about the nature gives us a lot of time series that are also visually relatively easy to forecast, like wind speed, temperature, sunspots. If you look at this, you can look at it and more or less analyze it even without any formulas or with some really linear assumptions. And the problem is the statistical features, geometrical features, the compositions, the statistical models, they're a way too simplified view of the world. They were created to describe the data like 40 years ago when you had limited observations, but now, based on also this more high-frequency data, we see more and more non-linear things. And the natural, why I showed the slide with the one matrix and a lot of matrices, the natural expansion of the one linear operator is the combination of linear operators with some non-linearities. And that's the simple deep neural network. That's the just one step ahead. And actually, that's what I'm saying, that if you want to model something a bit more complex than linear and non-linear, thanks to the universal approximation theorem, we have simple multilayer perceptron. And that's it. And actually, it comes out that in practice, with this kind of time series, you don't need some deep recurrent convolutional stuff. Because this data is simple by its nature. Don't overcomplicate it. MLP works just fine. And if we talk about some local geometrical patterns, yeah, convolutional networks look better because convolutions are aimed to model the small patterns. For example, in the ECG domain, if you want to spot some missing peaks or something, that's the convolution. Convolution is looking for some particular part. If it found, okay, it fires. If it didn't found, it didn't fire. So that's when I'm talking geometry, it's convolutions. Okay, this is about what looks good to us visually. And there are successful use cases. For example, if you check out these competitions on Kaggle, you can see that actually deep learning took the first places in this kind of time series competitions. And for example, what inspires me is a person that works with cardiograms. Stanford, their ECG model, they beats the doctors in terms of accuracy. And the first two cases can be done with multilayer perceptron. Second, deep convolutional networks. Seems to me good results. But okay, this is visual analysis. There are also time series that is really hard to analyze visually, but they have the patterns that are kind of hidden on the frequency domain. So basically, if you do some Fourier transform or you apply some wavelet analysis, you see some frequency-based patterns. But when you look at it visually, it's kind of not clear what it means. Okay, if you really work a lot with this data, you already see the patterns, but on the first sight, it's kind of hard to spot. That's why, but you can see the really changes of the frequencies, especially clearly seen on the second of the accelerometer data. You can see the different classes, but when you apply some frequency-based analysis, you can basically model it. And if you remember Fourier transform, convolutional theorems, and blah, 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 it also comes naturally what neural networks have to apply here. The problem with the Fourier transform and the wavelet transforms that this is the fixed basis. You model your data based on some fixed assumptions of your data. The idea, again, the nice property of convolutional nets, that they're connected theoretically to the Fourier transform, but their convolutional basis is to be learned. So basically, your assumption is, okay, that I have this kind of filters, this kind of patterns, I want to learn them. And that's also a natural expansion of the frequency-based analysis. Instead of having the fixed basis, you learn the basis. It's natural step ahead that you have to learn the same stuff you had before. The same as NLP. You had one linear formula. Now you have combination of linear operators with nonlinearities. Okay, a bit bigger step ahead, but still it's not that difficult. And another couple of nice use cases. First one is from Uber. Really recent work, what they do, they analyze, Uber Eats, the food delivery. They have to analyze, okay, don't distract you with the G. You have to analyze the delivery. Basically, the guys on the bikes, on the, even maybe the cars, the public transport to deliver the pizza. And there can be some delays. Maybe they are staying and waiting for the pizza to be done. And the problem that if you want to track with GPS, it's inaccurate. And some people have old phones, so you can't actually track where is your pizza based on the GPS. But based on how you walk and have your phone in your pocket, you can see the patterns. Are you on a bike? Are you on a scooter? Are you walking? Are you waiting? And that's what they did. And that's how they actually improved the timing of the deliveries and they assigned the right people to the right deliveries. And again, how they analyze the data from the accelerometer. That's how they do it. It's really recent work from, I think, maybe this month or 1 month ago. And if you're talking about the sounds, actually our sound looks like this, which is also time series. And there is a nice algorithm from DeepMind. It's WaveNet architecture. We'll touch it a bit later. It's also convolutional network, in fact, but autoregressive one, which is became, I would say, the baseline for speech processing. Not the latest thing, but the baseline, definitely yes. Okay, there are some time series that look predictable. There are some time series that have some frequency-based patterns that we can spot with some relatively simple transforms. But there are also time series that we observe something, we observe some data, but actually how this data is created, what actually created this data is kind of hidden. For example, if it's accelerometer data, we know for a fact that there is the device, the small machine in your pocket that makes these movements. If it's a sales, we know, okay, it's a particular sale that some person purchased something. If it's ECG, it's from electrical circuit of your body. For example, in financial markets, when you observe a price, you actually don't really know what created this price. It was one big deal of some big fish, big whale in the crypto market. It was some common decision based on the news in the traditional market. You don't know what created it, but you have the price, you have the observation, and need to model this observation somehow based on some hidden state that you have behind it. And this is how this data might look like. So basically the problem that it can, basically there are a lot of people, especially in the finance, especially who are not really deep into mathematics, they're trying to find visual patterns, they try to find even frequency-based patterns, but the problem that they're trying to model data that looks actually stochastic, and they try to model data by the way how it looks like, not understand there is some hidden state behind, so they actually need to model the hidden state behind. And obviously there are some classes of the models that aim to model this, like hidden Markov models. There are even dynamical factor models. There are Kalman filters, I'm sure most of you studied in university. So basically the problem of these algorithms that if they're statistical learning like hidden Markov models, they're simple. They can't deal with high-dimensional problems per se. If you're talking about the Kalman filters, I think it's a really great tool, but it requires the model of the system. So basically you need some set of differential equations. So some another model that says, okay, this is how my system, dynamical system, supposed to behave, and I kind of model it. The solution might look obvious, recurrent neural networks, because they have the hidden state, you model it, they have another matrix in your equation, and it's also nonlinear, long-range dependencies. Theoretically, it can even model infinite sequences, which sounds really good in theory. But in fact, and it was observed, I would say maybe 1 year ago, something like this, that when you actually apply recurrent nets in real life and you want to see the, let's say, good performance, for example, you're really dealing with, okay, you understand more or less what is recurrent neural network at some point. Okay, more or less, guys, at least gets some idea. Basically, you model step-by-step dependency or even more than step-by-step dependency, depending on the equations. So the idea is, okay, I have this observation, I model next observation based on the past observation or observations and some hidden states as well. Okay, but if you want to apply this model in practice, and I have 10,000 observations, I mean, okay, I have the tool set for it. I have this recurrent neural network. But neural networks are trained with what? With backpropagation. So if I want to train this neural network, I'm taking my gradient from the very last step, and I have to backpropagate it through the 10,000 steps. It's literally like training a 10,000 layer neural network. And that's what we don't really want to do. Even having the residual neural networks, it's not really what we want to do. So again, what I'm going to show now, it's empirical result. There is, let's say, no nice theoretical basis for it. But empirically, autoregressive networks, basically this is some kind of architecture that also takes the previous observation or previous prediction into account to predict the next one. But autoregressive convolutional networks, they don't need that much backpropagation because it's in the basis, it's not recurrency, it's convolution. Okay, so just imagine that you have like WaveNet, the convolutional network, but the problem is this convolution, you know that the convolution has some filter, basically it goes on the time series, on the image, and you try to find some patterns. But the theoretical nice property of the recurrent network that you want to learn any length of the pattern, this infinite length neural network. So the trick, and again, this is the empirical thing, that there is a thing called dilated convolutions. Just imagine you have a convolutional filter of the size 3, and it goes on your time series, and try to find some pattern on the size 3. And how to make it larger? Okay, you can make it the size 6. You go with the size 6, size 10, size 100. But this way, it gets too complex. The dilational convolution, it's when you have the same 3, but with the holes. So this way, it allows you to model wider context, and you have enough filters of this size 3 but larger context, basically you can model really long-range dependencies. And also they build the architecture that on the first layer, it can be like context of the range 20, then 10, then 5, then 3. So this way you both learn wide context, and with the depth of neural network, you could make it narrower, so it makes sense in any way. But I'm sure that if you talk about autoregressive networks, maybe you heard about transformers and GPT-2 and BERT and everything what works today for language. Okay, basically this is also autoregressive network, but the idea is that for transformers, the designers of this model, they decided, okay, recurrency, it has the problem. Basically, they created for text originally. So they say, okay, if I want to model long text, the paragraph, I'm not going to put it in the recurrent neural network because it can be 1,000 words, 10,000 words. I'm not going to do it. If you're talking about the convolutions, yeah, I can make like dilational convolutions to model different word combinations. But actually, language, it's not linear. You don't really model the language with the triples of words or something like this. That's what people thought, again, 40 years ago with the n-grams, but that's not really how the language is built. So they made a bit more complicated architecture that's basically inside it based on the multilayer perceptrons, made the model so-called attention, basically the co-occurrency of the words in a way, over any context, over the whole sequence. It's different architecture. I'm going to dive into it, but basically, yeah, it made the nice results, and basically this is state of the art today in the language modeling. So for us who work with time series, it makes sense, like let's use this model because it actually gives state of the art with sequences that are texts, but there is a big problem with transformers. Because transformers are designed, they totally lose the idea of some local patterns, and we know that time series, there are local patterns. They totally lose the idea of the, let's say, step-by-step dependency of the recurrency, but we actually know that at least in some time series, there exists this dependency. Then they say that there are some words that usually stick together on some different levels of hierarchy, and we want to model this. But in time series, do we actually have that? Then can we say that in this time series, there is some correlation between two observations, that they should go together? Not really, because in the language you have two words, two synonyms that go together. And the problem is that, yes, second point, we don't model time series like this. And the first one, BERT and GPT-2 and transformers, they work with embeddings. They don't work with, let's say, single time series observation. They work with the word embedding that already has to have some sense. So, because these embeddings, they're also supposed to model the similarity between words in different contexts. But how do you say that, okay, this is one point of cardiogram, this is second point of cardiogram, this is sale in December, this is sale in January. What is the similarity? They're not words. I can't say that this 65,000 sales in December correlates with 67,000 sales in January. It makes no sense, this definition. But between words, it makes sense that the words nice correlates with the words good. And there are some vectors, some embeddings that show it. So basically, I experimented with transformers, and the only situation where I found them useful, but it was kind of hacky. Basically, if I have some short time series, maybe like a short phrase, like 30 observations, and I apply forward over this time series, I use, for example, LSTM, because I assume that there is some hidden state. And from the end of LSTM, I get some kind of embeddings. So basically, even I have the observation of the dimension 1, I run it through the LSTM, and I get, for example, for each time step, I get the embedding of the size, let's say 100. It's some sort of embedding that some sort of encodes something about my time series. And if over this I apply one or two transformer layers, it gave me one boost of the analysis of the heart rhythm, even not ECG, but just the rhythmography. And the boost was not really significant. So I think transformers are not really for the time series yet. Okay, we talked about classification, regression. This is the classical stuff we solve today. Basically, that's, I would say, maybe 80% of the tasks. Another maybe 15 or 10% of the tasks when you deal with time series is anomaly detection. And in a lot of situations, it can be in medicine, can be manufacturing. For example, this is example of a couple of samples of it was a dataset on network intrusion. Basically, what behavior in the network is regular, normal, and what is anomalous. For example, up is the, let's say, normal, and below is some anomalous behavior in the network. And how to differentiate it. And especially when you work with anomaly detection, most probably you have a lot of data that looks good, that is regular behavior of a system, but there is some outlier that, okay, you don't really know how to model it because it also can change over time. Basically, the intrusions can be different. And okay, you can have, you can't really gather the data set because most of the time you have normal behavior, but sometimes you have this anomalous thing that can basically ruin your business or make you big losses. So how do you model it? Maybe something unsupervised, maybe some statistical. There are some approaches, of course, and there are some, you see the list here. But the problem, again, that's the linearity, and there is nothing really designed for a time series. Or if it's designed for a time series, originally it's based on the statistics, some rolling statistics, or you feed some ARIMA and check the residuals. Okay, you have some time series, you feed some statistical model and say, wow, it doesn't fit good enough. Maybe it's the outlier. But again, we talk about statistical models. And what I want to offer you guys here is, I think, and I really tried a lot of tasks, autoencoders and generative neural networks for anomaly detection. When I was talking about this 1 year ago, it was kind of new. Today, they're already much more proved thing. So today, I can say it can be a new baseline if you have enough good data. So basically, what is the idea? What is the autoencoder? Just a couple of words. Autoencoder is a neural network that takes any input, can be image, sound, time series, text, whatever, of some relatively high dimension. For example, time series of the length 100. Then you apply any neural network you think is right. If you think it's simple time series, you apply NLP. You think it's cardiogram, apply convolutional net. You think it's some financial time series or something related, apply LSTM. You think it's something different, apply autoregressive network. And from this 100, you build your neural network in such a way so you squeeze this 100 to some lower dimension. Let's say 10, 20, 5. The idea is that from these 100 observations, the really useful information that it contains can be squeezed into the lower dimension. And how do you actually check that this is true, that this hypothesis I'm saying is real? That if from this low dimension, you can again reconstruct the original time series. So if you have the time series, you squeeze it into dimension 5, you can say, okay, that's something, it has nothing inside. But if from this 5, as you can see this here on the image, from this light blue cyan compressed feature vector, you can again output the original time series, then actually, yes, you can squeeze your input sample into dimension 5 or 10. And actually, in this dimension 5 or 10 or 2, like on this image, is contained the all information about the time series. Okay, that's nice toolkit. Maybe you can use it for squeezing something, but how do you use it for anomaly detection? That's the question. Someone knows about it already? Okay, then I tell you. When you train this autoencoder, how you actually are sure that what you train from the output looks as real, not as real, as the same as the input. Basically, you take the input, the output, and compare them somehow, based on some mean squared error, I would say, for example. And you want to minimize their error. So in the perfect case, when you squeeze something and the out squeeze, it's literally the same time series. So the error has to be really low. And you train this model on the nice normal behavior of your system, regular one. And now on this regular system, this autoencoder works really well. The error is close to 0. But now what happens if some another behavior you put as the input to this neural network that's already trained on your good data? It's squeezed in to a small dimension. Again, it outputs, but this neural network never saw this anomalous detection. It never seen it. So that's why when you compare again the error between the input and the output, the error will be high. And basically all you need to do is just tune some threshold. If basically you at the end of over this neural network you set a rule. If the error of recovery my input time series is too high, it's an anomaly. This simple. And for example, again, in my case, it worked in ECG analysis really well. Basically, when you measure the cardiogram, you can move, you can talk, you can do too many things. And basically, you have to detect if it's not ECG at all. Because if you move, the signal is corrupted. And for example, we applied autoencoders for this. Really small neural network, it works fine, and it works well. Okay, this is one way. But the problem of this approach that you have to tune the threshold anyway, and people don't really like it because maybe the threshold you have to tune dynamically. Maybe some new anomaly comes and you need to change the threshold. So it's kind of like fitting the ARIMA and tuning the threshold, but now you feed the neural network, which is kind of better, but still you have to tune it. So another idea I would like to show you is to use generative adversarial networks for this problem. How they work. Basically, that's the models that today they generate these images. That's the state of the art for generation. How they work. Basically, the idea is to have some neural network that generates something really good looking. But how do I measure this good lookiness? That's the open question because there is no loss function. There is no mean squared error that tells me this is a realistic image, this is sound is realistic, this time series is realistic. So the idea is, and this is the G generative model on the graph on the right. So G is generator that takes something random on the input and outputs something realistic. And then instead of having the loss function, the idea is to apply the D stands for discriminator, the neural network that actually has to learn what is real, what is not, instead of your loss function. And you pass, for example, once you go with the something what is your initial generator not trained, it samples something, it creates some image, but of course, if it's not trained, it looks super bad. And you take some couple of nice looking images from your real data. And then your discriminator has to train, okay, this is something what is real, this is not real. And at the end, you use the feedback from discriminator to teach the generator. So generator, it learns how to fool the discriminator, and discriminator is actually trying not to be fooled by generator. And at the end, what is nice thing about these GANs, that the discriminator has 50-50 accuracy. Because the generator is so good, so it generates so realistic images, sounds, time series, whatever, the discriminator can't say what is real, what is not real. And that's actually where we stop and say, okay, we know how to generate something. But okay, one step back, we're talking about anomaly detection. Where is anomaly detection here? The point is that the discriminator over the training time saw so many random stuff that over time it automatically learned how to generate real stuff from the data set from not real stuff from the data set. So at the end, you come with the anomaly detector for free. This discriminator is the model that already says real, not real. And in our case, real is what was in the original dataset of normal behavior. So you have this automatically for free. You don't even need to tune it. It already has the highest possible accuracy of detection of the real, in our case, normal behavior. And again, 1 year ago, it was like, wow, new idea. Today, you can find 50 papers on this in different domains, both on the autoencoders and GANs. So it's more or less normal today. Next thing, sometimes we need to generate time series. Actually, there are not so many use cases. The use cases I encountered myself was in the financial domain. So basically, when you need to, okay, you have some prediction model, have some strategy, and you need to test it. The problem is how to do it now. If you test it on data on the past, you're in the risk that you have your model just works in the past. You can generate some artificial time series based on the stochastic models, based on the time series models. But again, these are the mathematical models. And they're, in a way, not real. So you never, okay, this is the model of some jump diffusion model. But you never can tell that your market will behave actually like this. So you can't test your models, your trading system, on the stochastic model, on the differential equations. The idea is to generate something that looks as most real as the market. But just to test the strategies. And actually what we did, we just pre-implemented the paper. It's called QuantGANs. And that's the use case. Basically, you can use GANs, you can use autoencoders, the different generative models. I just want to show the use case that generating time series is also can be needed. And by the metrics, the different like distributional-based metrics like Earth mover distance, blah, blah, blah. The time series generated by a neural network, TCN, by the statistical measures, they are more real to the real market than some statistical models, than some stochastic models. So generating for some simulation, for some testing, it's also a nice way to use generative models. Basically, variational autoencoders and GANs is what you need. Basically, how we did it, we just take something from the GitHub on the PyTorch that used for the images, replace 2D convolutions with 1D convolutions, tweak it until it works. So this is kind of really fast to go, and it works. Okay, another case also that is maybe less common, but it's still needed and used in time series analysis is to match in some things. Basically, in some domains, you have some pattern, some predefined pattern, like based on your knowledge, and you want to find this pattern among another samples, among time series. It also can be used for the search of the things. Basically, I have a database of some samples, and I have one new sample, and I want to find this sample is the most similar to what samples in the database. As an example, like fingerprints. I have a database of the fingerprints. I have my fingerprint, I need to find it or the most similar one in the database. So somehow I need to build some metric, some distance between my fingerprint and all the fingerprints in the world. So when I calculate the distance between them all, I find what is the most close one. A couple of use cases from my practice, again, biomedical time series. In the brainy time series electroencephalogram, you need to find some patterns in the time series. It looks literally like this. And the ECG, it was actually what I said about fingerprints. I was developing a project for a Ukrainian bank. Basically, they were trying to authenticate people for payments via ECG. So basically, they used our bracelet. And okay, if you want to do the payment, you don't put your finger, you don't use your face, you don't use your voice. You just put your finger on the bracelet, 2 seconds, and you're authenticated based on something they can steal your heart, basically. And how to reproduce electrical circuit from your heart, well, it's kind of difficult to do. So it's secure things, accurate. But in looking deep inside, you match the heartbeats of people. Basically, the technology itself, you need to somehow to compare the heartbeats of the people, and actually theory and practice says that we have all unique heartbeats, which is interesting. But again, we need some toolkit for it. And for this case, I want to offer mainly 2 things. if you remember, we were talking about the autoencoders, that they're able to squeeze the input sample, for example, this pattern or maybe this heartbeat, to some low-dimensional thing of size 10, 50, 5, doesn't matter. The cool part that when you look at the time series and you want to compare them, it's really hard to find the right metric, because you can't do like A minus B. You can't actually literally apply some Euclidean distance to it. You can't apply directly cosine distance. It's not trivial. You can't just subtract two time series and say, okay, they're same or not the same. And when you apply these autoencoders and you transform this initial time series into something, some hidden knowledge, basically the rules of the hidden knowledge and how the neural networks train inside, they all work in the metric spaces. So this squeezed representation is already where you actually are allowed to apply some normal distances, because that's how you train the models. That's what they're designed to do. It's normal. So you're allowed to do it. And then you can compare the samples in this small squeezed space of any size you want. But another nice idea, apart of using the autoencoders, is to use CMEs neural networks. So I want to make even one step further, and I'm saying, okay, yeah, it's kind of cool to squeeze it or to compare, but when I squeeze it, I don't learn directly the similarity, because, okay, I have a nice representation. I actually can do subtraction. I'm allowed to do it, but I am not sure, because I was training the model just to squeeze the information. Squeezing doesn't mean similarity per se. So I want some model that can give me something what I can say, okay, this is like really, this is similar and this is not similar. And okay, so the framework is this. I have, basically I want a formula for a distance. Some function from A and B that returns me distance between them. Like, for example, f from A and B equals A minus B. But in my case, it will be neural network. So I have two inputs to the neural network, and the output should be how similar they are. And this is what happens when you train a CME's neural network. Basically, it has kind of two sleeves. And again, these two sleeves, these two neural networks, they share the same weights, because if you want a distance between A and B and A, it should be the same. So basically, that's why the weights are shared. And again, the encode, these two sleeves can be any neural network you want. It can be LSTM, it can be convolutional, and MLP, whatever you want, based on your time series. And at the end, you already learn and you have these two samples. The problem here, you need to have a labeled data set. You have a data set that says, okay, these two guys are similar, these two guys are not similar. 1, 0, 1, 0. It might be a problem, because maybe you not always have this data set. But if you have it, you directly learn the similarity. And the similarity, the loss at the end, it can be mean squared error, it can be cosine distance. Basically, you choose the similarity you want. And this is the really nice point, because you literally train your own distance between the objects. More use cases. When we talk about the time series, very often they're noisy because of different reasons. In the financial market, it's mainly all noise, as we all are convinced to do. In the ECG, for example, you measure in some bad condition, there is some electrical interference from some devices, there can be noises. In manufacturing, can be noises. Basically, there are a lot of things that make the signal not good enough. So now we are dealing with the question. We have signals that are clean and signals that are not clean. And in computer vision, we had another interesting thing. We have zebras and horses. And how do we translate zebras to horses? There is a nice neural network architecture called cycle-GAN. Basically, it's the neural network that is maps totally in an unsupervised way. Basically, you have 1,000 horses, one data set. 1,000 zebras, totally another data set, and it learns how to map them into each other. The coolest part here, guys, that it's completely unsupervised. You don't need to label the data. You just need one source of noisy data and one source of clean data. And it maps automatically. Basically, this is kind of novel area of research. This is something what is new today, but I'm sure in 1 year everyone will do it. But for example, in our lab, we kind of move towards it. And this is our proof of concept, again on ECG. We made some extremely noise data set of ECG. Basically, it was clean. We noised it a lot. It was like combination of additive, multiplicative noises and some spikes. And there was a clean data. Not aligned, not paired. It was unsupervised learning. And actually, it learned pretty adequately how to filter out most of the noise. Yeah, there are some, as you can see, it's not perfect, but what is left, you can easily fix with standard filters. But taking account the noisiness of the initial signal, it was trained fully unsupervised. There's two separate data sets. It's good enough. But we decided to go further. Because in our case, what doctors are asking us, if you have medical quality of your signal, they don't think in the terms of additive noise. They say, I want my signal to be like medical device. And what we did, we have a data set from medical device, one set of people from the clinics, and we have data set from our device, which is a wristband, from people on the streets, people who just bought it and use it. Voila. Here we come to the domain adaptation. We have domain of medical device, we have domain of, let's say, wristband device, and I want to map wristband domain to medical domain. Two totally unsupervised different data sets. The samples, the result you can see here. Pretty adequate for completely unaligned, unsupervised learning, as for me. One more interesting case. Again, in medical domain, doctors, they want interpretation. Basically, if they say, okay, we found atrial fibrillation for this person, why did you find it? And we need to say, okay, because when he was recording yesterday at this time, and the 25th second from 55th to 55th second of his recording, we saw some of the waves missing. That's why our algorithm says that it's atrial fibrillation. The doctor says, yeah, that's what I would say as well. I suggested just to Google interpretation of convolutional neural networks because we're running a bit out of time, but the results are literally that, again, the convolutional neural networks that we apply for the cardiograms, again, by the rules and idea of the show slides before, after interpretation, they learn medical patterns. Basically, it highlights for the healthy people these waves. That's the waves that people actually who are healthy, they have them. So our algorithm is saying, this is the healthy person because these waves are present. And another side, what is the atrial fibrillation, where the rhythm is irregular, it points on the high peaks because that's what shows for the rhythm. It says the rhythm, look guys, I think this person is not healthy because look on the rhythm. And after this simple rule-based system that turns this visualization into concrete interpretation to the doctor. Again, you can Google CNN interpretation GitHub, it's open source code. The question for you now again, guys, what do you think now? Is deep learning the final frontier for this kind of tasks, today at least, or still not convinced? Okay, yes, who says yes? I'm wrong or less people now? Okay, who still is convinced that mathematics, stochastic models, domain knowledge? Okay. For you guys, I have a couple of more slides. Okay, yeah, there's also failed stories. Yeah, there are data sets when people took 100 observations, they applied their deep learning, and they say, wow, deep learning didn't work on 100 observations. And they say, wow, deep learning doesn't work. Okay, on 100 samples, nothing works actually. So this is just a slide for you to check out this big work when people try to hype a lot that deep learning doesn't work, and then check the data sets. So that's just a slide. Okay, for you guys who still want a name to use, let's say, domain knowledge. There is a nice framework how to apply deep learning alongside with some features that you consider correct from your domain knowledge. I know, statistical models, stochastic models, some formulas, doesn't matter. The idea sounds pretty simple. You just take your autoencoder features alongside with your normal features and train on this jointly. It can work out, but actually there is a problem. We try to apply this again ECG analysis. For rhythmography, it's nice to model entropy of the signal because it has some proven properties to model some of the rhythm abnormalities. Problem is that to calculate entropy in real time on the long sequences, it can be complex. And actually, we didn't really didn't really want to bother us with re-implementing things on the mobile phone or on the wristband. Basically, we didn't want to do this. So how you have some nice features, but it takes, for example, 20 seconds to calculate it. So basically, you can't run it in real time because you need to calculate the feature only after you run the inference. How do you do it? How do you kind of make a trick to still make your model know about this feature, but not calculating it every time? The trick is the following. If we know that deep neural networks are universal approximators, so basically theoretically they can model any function, why they can't model also additionally, for example, entropy? The idea is that you have your model that is trained, for example, on the raw time series as CNN, RNN, whatever, but a part of your loss, for example, for prediction, for classification, for whatever you have second loss function. Basically, your neural network has two outputs. One output, for example, is for the forecasting. Second output for prediction, the entropy of the sequence. And the idea is in the training time, you need to generate the data set. It takes a long time. You have this entropy as the output. But this network is able to approximate entropy as well. It has enough capacity in it. So this way you assure that your neural network knows about entropy. It doesn't know it per se as the input, but if from this sequence it knows how to output the entropy with the correctly enough, it means it takes it into account. It is regularized by knowledge of the entropy. And this is a nice trick, and actually it works. I have even a blog post on this. You can check some real examples of this particular thing. When I'm trying to show where that this multitask thing, having several tasks, works as regularizer, domain-based regularizer. And there's some results that multitask works better than baselines. You can check it later. I didn't talk about reinforcement learning, about dynamical systems, some differential question analysis, Bayesian deep learning, using the denoising autoencoders for missing data imputation, the neural-based ARIMAs in Facebook. Sorry guys, we have just 45 minutes. I'm already running late. So takeaways. When you use deep learning, apply it correctly based on the data nature. So that's basically my first slides. If it's a hidden state, use RNNs. If it's some geometrical features, CNNs, etc. Thumb rule, I think that CNN is fairly good baseline because CNN is more or less the same as the feed-forward neural network, so you don't mistake if you run it. But I think it's a nice baseline anyway. Generative models. I hope I could show you enough use cases where generative GANs, autoencoders do a lot of alternative things really well. And if you want to use classical models as well, a couple of minutes showed that there is a way to add these features, this domain knowledge, alongside with deep learning. Okay, that's all. Thank you for listening. I hope it was interesting and useful. Thank you, guys.